Let's work with some identities. We want to find the exact value of the sine of 75 degrees. We need to take 75 degrees and break it into 45, 60s, or 30s so we can find the exact value. Now 75 degrees is exactly 45 plus 30, and so I'm going to use that to sum. If I'm looking for the sine of 75 degrees, I can find the sine of 45 degrees plus 30 degrees, since that's the same. Now applying the sine sum identity, this is going to be sine 45 degrees cosine 30 degrees plus cosine 45 degrees times sine 30 degrees. And now I'm going to put in some exact values. The sine of 45 degrees is the square root of 2 over 2. The cosine of 30 degrees is the square root of 3 over 2. The cosine of 45 is square root 2 over 2. The sine of 30 is 1/2. And all I need to do is simplify. Square root 2 times square root 3 is square root 6. 2 times 2 is 4. Square root 2 times 1 is square root 2 over 4. The fractions have the same denominator, so finding their sum, I write square root 6 plus square root 2 over 4. Well, let's continue this idea, but now we want to find the exact value of the tangent of 7 pi over 12. So I have to take 7 pi over 12 and consider it to be a sum or difference of angles whose trig function's exact values that I know. Well, it turns out that 7 pi over 12 is pi over 3 plus pi over 4. In terms of pi over 12s, that's 4 pi over 12 plus 3 pi over 12, which is 7 pi over 12. So if I'm looking for the tangent of 7 pi over 12, I can find the tangent of pi over 3 plus pi over 4 and apply the tangent sum identity. So this is going to be, applying the identity, the tangent of pi over 3 plus the tangent of pi over 4 over 1 minus the tangent of pi over 3 times the tangent of pi over 4. And now I need to fill in some values. The tangent of pi over 3 is exactly the square root of 3. The tangent of pi over 4 is 1. And underneath that then, using the same values, tangent pi over 3, tangent pi over 4, I'm going to have 1 minus square root 3 times 1. And so this is the result, but I want to rationalize that denominator. So let me write that on another sheet. What I have at this point is square root 3 plus 1 over 1 minus square root 3. To rationalize the denominator, I'm going to multiply the numerator and denominator by 1 plus square root 3. In the numerator, I end up with, if I multiply it out, square root 3 plus 3 plus 1 plus another square root 3. In the denominator, I end up with 1 minus 3. It multiplies to become 1 squared minus square root 3 squared. Continuing to simplify, the numerator is 2 square roots of 3 plus 4. The denominator is negative 2. If I factor a 2 from the numerator, from each part of the numerator, I have that 2 times square root 3 plus 2 divided by negative 2, and a factor of 2 will simplify. So at this point, I have square root 3 plus 2 over negative 1. And I'm going to pull the negative 1 to the numerator and distribute it, and call this negative square root 3 minus 2, and that's the simplified version of the answer. Well, there's one more part to this example that we're working on. We want to find the exact value of sine 40 cosine 160 minus cosine 40 sine 160. And what we're looking at is a sine cosine minus cosine sine, which matches the sine difference identity, sine of A minus B. Recall that the identity is sine A cosine B minus cosine A sine b. And what we are looking at in our example matches the right-hand side with a equal to 40 degrees and b equal to 160. So if we take the right-hand side and work to the left-hand side, we end up with the sine of 40 minus 160, 40 degrees minus 160 degrees. And simplifying, that's the sine of negative 120 degrees. Recall that the sine of negative theta is negative the sine of that angle theta. So I have negative sine of 120 degrees. And the sine of 120 is the square root of 3 over 2. And that's the result of sine 40 cosine 160 minus cosine 40 sine 160.
Write the function as an expression involving functions of theta. We have the sine of the quantity 30 degrees plus theta. So we will use the sine sum identity to rewrite this as being equal to the sine of 30 degrees times the cosine of theta, then plus the cosine of 30 degrees times the sine of theta. But now we can evaluate sine of 30. Sine of 30 is 1/2. So we have 1/2 cosine of theta. We can also evaluate the cosine of 30 degrees. That's the square root of 3 divided by 2. So this would be plus square root of 3 divided by 2 times the sine of theta. Now we have two fractions here. They happen to have the same denominator already. So what we can do is add the numerators. So this would be equal to, of course, 1 times cosine theta is just cosine theta, plus the square root of 3 times sine theta, all over 2. And now we've written that function as an expression involving just functions of theta. Let's work another example. Write the function as an expression involving functions of theta. And we have the tangent of 45 degrees minus theta. So in this case, we'll use the tangent difference identity, and we'll write that this is going to be equal to the tangent of 45 degrees minus the tangent of the theta divided by 1 plus the tangent of 45 degrees times the tangent of theta. We can evaluate the tangent of 45 degrees, which is equal to 1. So we have 1 minus the tangent of theta in the numerator. And in the denominator, we can evaluate tangent of 45 degrees, which is 1. 1 times the tangent of theta would simply be tangent of theta. So we would have 1 plus the tangent of theta. And when we look at this expression, it is now involved with just functions of theta, and we've completed that example. Let's work another example in which we rewrite expressions. Write the function as an expression involving functions of theta, and we have sine of the quantity 180 degrees minus theta. We'll use the sine difference identity, and we'll write this as the sine of 180 degrees times the cosine of theta minus, then we'll have the cosine of 180 degrees times the sine of theta. Let's evaluate the sine of 180 degrees. That's equal to 0. So we have 0 times the cosine of theta minus, evaluating the cosine of 180 degrees, that's equal to -1. So we have -1 in parentheses times the sine of theta. 0 times anything is 0. So this part of the expression is 0. When you're subtracting a negative, that is the same as adding a positive. And so this would simply be 0 plus sine theta, which is equal to sine of theta. And we've completed that example.
Let's work with some identities. Suppose that A and B are angles in standard position with sine A equal to 4/5 and A between pi over 2 and pi, which means that A is in quadrant 2. Cosine B is negative 5/13 and B is between pi and 3 pi over 2, which means that B is in quadrant 3. We want to find the sine of A plus B. We are not ready to jump right into finding the sine of A plus B. What we need to do, we have sine of A, is find cosine of A. We have cosine of B, we need sine of B. One way to do that is to use the Pythagorean identity that says that cosine squared, and let's start with A, plus sine squared of A is 1. Well, I know that sine of A is 4/5. So cosine squared of A plus 4/5 squared is going to be 1. So I'm solving for cosine of A. Cosine squared of A plus 16/25 is 1, and I need to subtract 16/25. So cosine squared of A is going to be 25/25 minus 16/25, which is 9/25. And I'm ready to take square roots. Now I have to think through. Cosine A is both positive and negative, the square root of 9/25, which is both positive and negative 3/5, and I need to decide which of these to keep. So I look back here and I see that A is in quadrant 2, cosine's negative in quadrant 2, so cosine A is negative 3/5. Now I need to do all of that again, given cosine B is negative 5/13. So I have cosine squared of B plus sine squared of B is 1. Cosine of B is negative 5/13 squared plus sine squared is 1. Now I square the numerator, I square the denominator, and I'm looking for sine of B. So I'm going to subtract 25 over 169. So sine squared of B is going to be 169. Maybe I'll write this one down, minus 25 over 169. So sine squared of B is going to be 144 over 169, and I'm ready to take the square root of each side. So sine of B is both plus or minus the square root of 144 over 169. So sine of B is both plus or minus 12/13. To decide whether it is plus or minus, recall or look back and note that B is in quadrant 3. Sine is negative in quadrant 3, so the sine of B is negative 12/13. So I've written down what we've already determined, and our actual problem is to find the sine of A plus B. Using the sine sum identity, that means we need sine of A, cosine of B, plus cosine of A times sine of B. And these are the values that will fill in. I have sine of A is 4/5. Cosine of B is negative 5/13. Cosine of A is negative 3/5. Sine of B is negative 12/13. And I want to simplify. This is negative 20 over 65 plus 36 over 65, and I find that sum, negative 20 plus 36, is 16 over 65. So the sine of A plus B is 16 over 65. Well, using the same values, I want to do this. I want to find the tangent of A plus B. Now the tangent sum identity, tangent A plus B, is tangent A plus tangent B over 1 minus tangent A times tangent B. But I don't have tangent A and tangent B at this point, so I need to find them. To find the tangent of A, I'm going to put in the sine of A divided by the cosine of A, the values that I've already found. Now, the sine of A was given, and it was 4/5. The cosine of A is negative 3/5. And if I multiply by the reciprocal, I end up with negative 4/3 for tangent A. Tangent B is sine of B over cosine of B. The sine of B is negative 12/13. The cosine of B was negative 5/13. And if I multiply by the reciprocal, I end up with 12/5. And so now I'm ready to find the tangent of A plus B. You can look back at the identity. What you'll need to put together is the tangent of A plus the tangent of B over 1 minus the tangent of A times the tangent of B, and we want to simplify. Going to the numerator, to simplify the numerator, the common denominator is 15. This will be negative 20 over 15 plus 36 over 15. And the denominator will be 1 plus 48/15. To continue to simplify, I'm going to move to another sheet. What I have is negative 20 over 15 plus 36 over 15 over 1 plus 48 over 15. The common denominator of all the individual fractions is the number 15. So I'm going to multiply the numerator and denominator by 15, and I'll end up with negative 20 plus 36 over 15 times 1 plus 48, which simplifies to 16 in the numerator, and let's see, 8 and 5 is 13 over 63 as a final result. Well, let's look at part C. Again, we have A and B angles in standard position and the same information as we've been working with, but this time we want to find the quadrant of A plus B, the angle A plus B. Well, what we've come up with so far for parts A and B are the sine is positive 16/65 and the tangent is positive 16 over 63. Well, the only quadrant where the sine and tangent are both positive is quadrant 1, so A plus B must be in quadrant 1. Let's verify an identity. We want to verify that the sine of pi over 6 plus theta plus the cosine of pi over 3 plus theta is equal to the cosine of theta. Well, I'm going to work on the left, and I'm going to start with the sine sum identity. So this part of the left side is equal to sine pi over 6 cosine theta plus cosine pi over 6 sine theta. That's sine of pi over 6 plus theta. I have that plus this cosine sum, applying the cosine sum identity, cosine pi over 3 cosine theta minus sine pi over 3 sine theta. So that's a first step. Let's work from there and put in some values for sine pi over 6, cosine pi over 6, cosine pi over 3, sine pi over 3. So I've copied that part on another sheet. I want to put in the value of the sine of pi over 6, which is 1/2. I have that times cosine theta. I want cosine pi over 6, which is square root 3 over 2, times sine theta. Plus, now, the cosine of pi over 3 is 1/2 times cosine theta minus the sine of pi over 3, which is square root 3 over 2, times the sine of theta. So I've put in some values. Now look what I have. Square root 3 over 2 sine theta minus square root 3 over 2 sine theta are going to add to 0. And 1/2 cosine theta plus 1/2 cosine theta is exactly 1 cosine theta or cosine theta. And if you look back at the identity we were trying to verify, that's what we were trying to show.